So picture this. It's a future where we're facing a planet that just keeps getting warmer, and everything we're trying on the ground, it just isn't enough. Today, we're going to look at a blueprint for that exact future. It's an absolutely audacious, long-term vision called Project Space Sunglass. And get this, it's not really designed for us, but for the generations that'll come after us.
Yeah, that quote really sets the stage, doesn't it? It's this powerful idea that to solve a problem on a planetary scale, what we might actually need to think beyond the planet itself.
So let's dive right in. Why on Earth would we even consider something as out there as a sunshade for the entire planet? Well, it really just boils down to two simple things: speed and scale.
Okay, now this is important. Things like renewables, carbon capture, they are absolutely essential, no question. But they're slow. They might just not be fast enough to stop us from hitting some really scary climate tipping points. So the Space Sunglass idea isn't about replacing those things, not at all. It's meant to be a complementary tool. You could almost think of it as a planetary safety brake that we could use while all the other long-term fixes on Earth really take root. All right, so how would this thing actually work? I mean, how do you give the whole planet just a little bit of shade without, accidentally starting an ice age? The basic idea is actually surprisingly elegant. It all starts right here, at what's called the L1 Lagrange point. The best way to think about it is like a perfect cosmic parking spot. It's about 1.5 million kilometers away from us, and anything you put there gets caught in this perfect gravitational tug-of-war between the Earth and the Sun. What that means is, it just stays put, always parked right between us and the Sun, which is exactly where you'd want a sunshade to be.
And this right here is the best way to explain it, especially to a kid. We are not talking about blocking out the sun or creating an eclipse, no way. Think of it more like a massive, see-through piece of cheesecloth just floating in space. It's designed to be mostly empty space, just enough to cut the harshest glare and take the edge off the sun's intensity, but without making our days noticeably darker.
So, here's the kicker. How much of a difference does this tiny little tweak actually make? Well, it turns out blocking just 1 to 2% of the sunlight hitting Earth would be enough to offset pretty much all of the warming that's been caused by human activity. It's a really small adjustment with a massive, potentially planet-stabilizing effect.
Okay, so the physics works on paper, that's cool. But the engineering, oh man, that's a whole other beast. How would humanity actually build something this enormous? Let's get into the nitty-gritty, the blueprint.
Yeah, this is a true multi-generational project. It's all broken down into these 4 methodical phases. You can see here, phase 1, just setting up the factories and mines on the moon. That alone could take 20 to 30 years. Then you have phase 2, building the whole supply chain to get all those parts from the moon out to the L1 point. It's only then, in phase 3, that autonomous drones start actually assembling the mesh, and even that takes 5 to 15 years. And phase 4, activation, that happens super gradually, unfolding over decades to make sure everything stays stable.
To really get a feel for this, let's just imagine it for a second. The year is 2150. An engineer starts their day, but not with coffee and a traffic jam. Nope, their day starts in a habitat on the moon, and they're looking out over this huge, silent factory floor where robots are just 3D printing components for the sunshade 24/7.
And where are all the raw materials coming from? Definitely not from Earth. It's just way too expensive to launch that much stuff out of our planet's gravity. Instead, you'd mine the moon, the lunar soil, what they call regolith. It's super rich in stuff like silicates and aluminum. And for the other elements you need, you'd go out and process asteroids, the moon's low gravity and lack of atmosphere. It basically makes it the perfect off-world industrial park.
So, how is this thing actually built? It's not one giant solid sheet. It's way smarter than that. It's a swarm of millions of individual little units they call S-pixels. Think of each one as its own tiny, smart, autonomous satellite. It's got its own solar power, its own little thrusters to move around, and an AI chip that lets it fly in perfect formation with all the others, creating one massive, controllable cloud.
And when you get all those millions of S-pixels assembled out at the L1 point, they form a single cohesive mesh with an effective diameter of 1,400 kilometers. The scale is it's almost impossible to wrap your head around. A true work of planetary-scale engineering.
So yeah, this is an absolutely incredible feat of engineering, but it also means we'd be creating a thermostat for our own planet. And that comes with a mind-boggling amount of responsibility. So it's time to ask the really hard questions.
Right? This is the first and most obvious fear.
With a system this powerful, what happens if something goes wrong? What if we miscalculate and overcool the planet, triggering a catastrophe that's even worse than the one we were trying to fix?
Well, the design has a really crucial failsafe built right in. That swarm of S-pixels needs constant active commands to stay in formation. If that control system were to just completely fail, the swarm would simply drift apart. The shade would vanish, and Earth would gently, safely return to its normal level of sunlight. It's designed to fail safe, not to fail deadly.
Okay, but that solves a technical risk. It brings us to an even trickier one, the human risk. Who gets their hands on the planetary thermostat? Who gets to decide if it's a 1.2% reduction this year, or maybe 1.3%? Who makes that call?
The blueprint is very, very clear on this point. It absolutely cannot be controlled by a single country or some megacorporation. The proposed model for governance is a global trust, something managed by international bodies like the UN, scientific councils, and all the spacefaring nations working together. The whole point is to make sure it serves all of humanity, not just one group.
And this table really shows the tightrope we'd have to walk. On one side, you have these ethical guarantees baked into the design. It can't be weaponized, everything it does has to be totally transparent, and any changes to the climate have to be incredibly slow and gradual. But on the other side, the challenges are huge. How do you really prevent misuse? And how do you get every nation on Earth to agree on how to use something that's powerful and keep them agreeing for centuries?
Look, the challenges are enormous. There's just no question about it. But the potential is also enormous. This kind of project is about way more than just managing the temperature. It's about fundamentally changing our relationship with our own planet.
Just look at the ripple effects. Beyond the obvious climate security, the act of just building this thing would ignite a true space economy. We're talking asteroid mining, manufacturing on the moon, and that would drive breakthroughs in AI, robotics, and material science that would totally transform life back here on Earth.
And this really captures the philosophical leap we'd be making. For pretty much all of human history, we've just been subject to whatever our planet's climate does. A project like this could mark a transition, from being victims of our environment to becoming responsible managers of it. And maybe, eventually, even thoughtful designers of our own world.
Which brings us to the ultimate question. The technology, it might one day be possible. The engineering challenges, maybe they're solvable. But the real question is, should we? Should humanity ever wield the power to intentionally dim our own sun? That's a question not just for scientists and engineers, but for every single one of us.